Okay, so you're able to do everything with arithmetic. I give you any numbers. You can add, subtract, multiply, and divide. Fractions, decimals, percents. You can convert between units. We're going to extend that now just a little bit. Let's make sure you can do it. I'm going to draw this little rectangle up here. I'm going to say it's 6 centimeters this tall and 8 centimeters like that. Your job is to find out how far it is if I started right here and went all the way around. You're like, okay, so you went 6 centimeters, then you go 8 centimeters is 14, you go another 6, that's 20, then you go another 8, so 28 centimeters. Let me write it out. Okay, distance all the way around equals 6 centimeters plus 8 centimeters plus 6 centimeters plus 8 centimeters. Okay, so 6 plus 8 plus 6 plus 8, and that's where we got 28 centimeters. Good. We're going to do another one just like that. So this is going to be 3 meters, and this is 15 meters. I want you to find the distance all the way around. 3 and 15 is 18, plus 3 is 21, plus another 15. So let's write this. Okay, I'm going to give you a new word for this. Peri means around. If you've taken any health science courses, you may have studied a pericardium, that is the surrounding membrane around the heart. Peri is just a prefix that means around, and meter means to measure. So the perimeter was 3 meters plus 15 meters plus 3 meters plus 15 meters. And we got 36 meters. Now, we could do another one just like this, and another, and you realize that we're following the exact same pattern over and over and over. And it never changes. You're always going to take this number plus that number plus that number plus that number. And it's always going to be the same. In math, that pattern is called a formula. Show what I mean. If we take this, we say, okay, we have a rectangle. This is the width, and this is the length. Then the perimeter would equal the width plus the length plus the width again plus the length. Okay, so you write that out, and that pattern, you write it out like that, and that's a formula. That's what a formula is. Now, some of you may have always wondered, and even if you haven't, it's good to ponder it, stay up late at night thinking about why did somebody decide to put letters and numbers in math at the same time? That gets kind of confusing. I mean, you're doing 6s and 8s and 2 5/3 and whatever. You have all these numbers, and then people start putting in X's and Y's and Z's and Q's and L's. Well, this is why. Right now, we have a pattern. We don't know what these are, but writing this out over and over and over again gets tedious. So we just say, hey, let's abbreviate the perimeter here. I'd use a P. Here, W for width. L for length. W for width. L for length. That's why they put letters in. It's just, we don't know what the numbers are. They could be a 3 and a 15, or they could have been a 6 and an 8 like we had before. That's what they put them in here. And since they can change, this letter could represent any bunch of numbers. They call it a variable. That's where variables come from. Is when you do a pattern, you can't specify what numbers you're actually using. You have letters that kind of take the place of them right there. So, in this case, we did 6s and 8s for the 6 for the width and 8 for the length. Now, dealing with variables, and you're going to be dealing with them for the remainder of the course, you need to know a couple of things about them. The first thing is when you're doing arithmetic, like we did in Chapter 1, you did something like 6 times 5, where this is how we wrote times. We now have, since we have letters that are possible, we might use x at some point, which means this might not be so good. And so we have a new symbol for times. And it means the same thing, it's just a dot, raised up in the middle. So we could write it like this, 6 times 5. So nobody ever thinks that we're using that as a letter instead of a symbol. 6 times 5. So if you did, for some reason you want to take 7 times the width. You take 7 times the width. We can't do that. You have an x and a w both in the same spot. So that's why they write it 7 times w. Or if you have a letter and a number, they can put things right next to it, like 7w. And these are the different ways you can do multiplication. You can write it times with a dot, or if two things are not alike, you can put them right next to each other. You can technically do it here. But you're thinking, wait, is that 6 times 5 or is that 65? Well, you need something to say, hey, wait, these are separate numbers. The 6 is by itself and the 5 is by itself. And so they might go like this. And say, this is a 6, that's a 5, and they're next to each other, so that's timesing. 3 times m, we wouldn't write that. We could write 3 times m or 3m. Good deal. Now, you'll see this is a really nice way of writing them, because in general we can take these variables and look at what happens with them. Way back when you did multiplication, you had 7 plus 7 plus 7. Well, that's 3 times 7. 21. What if I had an m plus an m plus an m? No matter what this letter is, we have 3 of them. So we say I have 3 m's. Now, keep this in mind. Let's go back and do some more addition like we did before. When we had 5 apples plus 2 apples, that equaled 7 apples. Notice these had to be the same. We couldn't do 5 apples plus 2 penguins and get anything. 5 apples plus 2 apples is 7 apples. Well, same thing. If I have 5 apples plus 2 apples, that's going to be 7 apples. If these two are exactly the same, we just add them up like that. 3m plus 8m, well, that gives you 11m, just like what we did. However, if you have 3m plus 2p, 3 marmots plus 2 penguins is, we don't know. That's as much as you can simplify stuff. When you take something like this, where these guys are like, they call them like terms. Oops. They call them like terms, and you combine them together, they call it combining like terms. You put those two together and you put it like that. So, do something that's way out here. You have 3xy plus 5m plus 2xy. And I say simplify that. Put it together. This is how you do it. You take this guy and that guy, and you'd have 5xy. Because they're exactly alike. You have 3 of them, 2 of them, that's 5 of them. That's how we combine like terms. The first thing you should know is that formulas were kind of invented as a way to make sure you always kept the same pattern. Let's say we have a certain rate of speed and a certain time. So we had, say you went 30 miles per hour and you did that for 2 hours. How far did you go? So, go 30 miles in 1 hour, and then you go for another hour at the same speed. You got 30 and a 30. You end up multiplying these two together. We did that with unit conversion. 30 miles per hour times 2 hours. The hours cancel. and we were left with 60 miles. Now if we did it again, say you were traveling 70 miles per hour, and you did that for 5 hours. You're like, oh, we times them again. So 70 miles, that's 350 miles. $70 miles times 5 hours, 350 miles. Notice we're doing this exact same pattern all the time. So we always, no matter what number is given here, we have the rate. And we always times it by the time. And that will always equal the distance. You just made up a formula. Don't write this out all the time. Pick a letter. I would suggest R. T for time. And here you have created a formula, which means every time you have a rate and a time, you multiply them together and you get distance. Another one that we've done previously is like taxes. Sales tax. If you bought something for $15, that was the price, and the tax rate, okay, the price is $15, the tax rate is, oh, let's say 6%. How much tax do you actually get? Well, percents are not real numbers, they're a portion of something, so you have to find out, okay, 6% of the original, so we take 0.06, okay, that's a percent into a decimal, times $15, and that equals our tax, how much tax there is. So that would be, oh, what is that? 15 times 0.06 is what, 0.90, I think? If you pull that out, punch that in your calculator, you get 0.9. So, sales tax on this is 90 cents. Now, think about the pattern that you went through. You took the tax rate times the original price, and that equaled the actual sales tax that occurred. You just made up your formula. Rate times price will always give you the tax. You could make up a whole bunch of formulas. It will take you a long time to make up all the formulas that you will need to know. Luckily, many people have gone before you and have made up several of them to let you know that there's an easier way. I'll give you an example. Celsius and Fahrenheit. Half of the world, well, more than half of the world deals with Celsius temperatures. Another portion of the world deals with Fahrenheit temperatures. And not everybody knows how to get back and forth between them. Here's how it is. The Celsius will always be 5/9 of the Fahrenheit minus 32. Now, do you know where that came from? Nope. And there's a long history. But somebody's already gone through and made that up, that you don't even have to do it. So if somebody says, okay, the Fahrenheit is, let's do 59. Fahrenheit is 59 degrees. Tell me what the Celsius is that corresponds to that. All you have to do is take this 59, put it in where that F is, and it will tell you exactly what the Celsius is. Show you how nice that is. 5/9, 59 minus 32. So we get Celsius would be 5/9 of 59 minus 32 is 27. So we're going to take 5/9 times 27. This is over 1. 9 and 27 leaves a 3. 5 times 3, 15 degrees. Fahrenheit 59 is the same thing as 15 degrees Celsius. And it came because when somebody had established a pattern, they wrote it back down and said, if you always take the Fahrenheit minus 32, times it by 5/9, that will give you the Celsius. That pattern is the formula that allows you to do math very quickly. So there are a lot of formulas that relate, rates and taxes and other things. And then the easiest, well, not the easiest, but the best thing for you is that people have gone through and given you formulas for all kinds of shapes. Let's do one we started with. Here we have the width, here's the length, we know that the perimeter was a width plus a length plus a width plus a length. Now, some people say, hey, wait a minute. A W and a W, we could have just taken two of those and two of those. And that's right. Two widths plus two W's. Some of you might even recognize and say, hey, there's a 2 everywhere. That looks like somebody distributed a 2 through. You're exactly right. If you take the width plus the length and times it by 2, that'll give you the whole perimeter. So they've just summed up how you get all the way around. And so this is a standard formula of a rectangle. They also have, on this particular one, the area. The area of that thing. So that, now when you're doing perimeter, you're measuring it in distance. It's kind of like you're stretching a really thin fishing line all the way around and you're measuring it like that. When you're doing area, you're trying to get everything in here covered. So it's more like with carpet or with square foot tile that you cover a floor or road size or something. The area. You can't measure it with a one-dimensional, just a length. You have to have a length and a width to cover that. So if you look at it, if this were, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if that were 10 and this was 1, 2, 3, 4, can you tell how many little squares of that would cover the entire thing? It would be 4 times 10, or whatever the length times the width. So here's another standard formula for a rectangle, length times width. Now you should note that perimeter and area are measuring something completely different. This is a one-dimensional object. Dimension meaning how many ways you can measure it. So here, when you get this, your answer will be in centimeters, or meters, or kilometers, or yards, inches, feet. Okay. Over here, you'll notice we're measuring with little squares. That's how we measure area and cover an area instead of just a length around. So when you get done here, they will be measured in little square centimeters. I had always wondered when I was a student, why in the world is an exponent of 2 called a square? And I think we talked about that earlier when we went over squared, but it's because it's actually you made a square out of a centimeter. And so that's what the units are for how you measure this. Centimeter squared, meter squared, kilometer squared. When you measure the size of your country, look in an encyclopedia, you look it up and it says, oh, this is 15 million square kilometers. You could have yards squared, inches squared, feet squared, and it just keeps going. Everything will be in square because you're measuring a two-dimensional surface. So if we make something that has, I don't know, 3 dimensions on it, let's see if we can make one of those. We have, alrighty, this is a cylinder that has a radius down here at the bottom, and it has a height here at the top. Now, the circle is a very common one that you're going to run into, and so I'm going to leave that for you to read about. But when you do this, you can get the area on the surface of it all around, or you can get the volume. Now, the volume is kind of interesting. It's like if you fill up the whole thing. Not if you cover it with squares on the outside, but if you actually fill it up with little itty-bitty cubes. And hence, that's where a 3-dimensional object is measured in things that are cubed, such as centimeters cubed or yards cubed. Concrete is often measured in yards cubed. This one's the one I'd like to talk about, so let's do this one. This is the formula. Let's see if we can look at what it is. There's this interesting number pi. Now, pi is not a variable. It's not a letter. It is a number that is about 3.14159, and it keeps on going forever. It's not the same as 22 divided by 7, but it's close. It's not the same as 3.14, but it's close. That number right there is a constant that was discovered long ago that we'll talk about in just a minute. This, we're going to take whatever radius they give us, like 7, and square it. So 7 squared is 49 times that, and then we would times it by the height. And what that would do, that would tell us how much would fill up this whole thing. Now, some of you, maybe you've been in health sciences or received a shot at some point where it said, oh, let's give him 5 cc's. Or you have known about engines. Engines are often measured in cc's, like a 100 cc motorcycle or 200 cc. cc stands for cubic centimeter. It is actually a centimeter by a centimeter by a centimeter. That's a 1 cc. If you go 1 centimeter, 1 centimeter, 1 centimeter. And 1,000 of these make a liter. So a milliliter is a cubic centimeter. Anytime you measure volume, it will be in a cubic because you're measuring length, width, and height, 3 dimensions. So let's go back and figure out what that number pi is and where it came from. Years and years ago, they had, way long ago, they had an interesting phenomenon with a circle. They would measure straight across the circle, which is called its diameter. From there, it's called the radius. So 2 of the radius, 2 times the radius would give you the diameter. But they would measure straight across, and then they would measure from here all the way around with a rope. And they would do this on small circles and huge circles and in between circles. And they found out that if they took this measurement all around the perimeter, the Greeks called it something else. They called it a which means around. That's the other root of measuring. So the around measure of a circle, and they divided it by its diameter. It always came out to be just about 3. Going all the way around there, if that was 15 feet, going across there would be just about 5. And they're like, really? Try it again. So they'd measure around and they'd get 21, and they'd measure across and it'd be just about 7. Not quite exactly, but close. And they would always do this ratio of the circumference to a diameter, and it would always be, a little bit bigger than 3. A little bit bigger than 3.1, a little smaller than 3.2. A little bit bigger than 3.14, a little bit smaller than 3.15. And so they called this number, or we call that number, pi. And so it's just a number that always happens with circles. So that means if you know what the radius is, the circumference will always be, well, if you double the radius and times it by this number pi, you'll always get the circumference. So there's your first formula dealing with circles. Notice if you have meters over here, the radius is measured in meters. Then if you take and times that by just over 6, you'll get all the way around. Kind of an interesting thing. Let's say the radius is 5. If you go pi times 5 squared, now you should take time right now to find your pi button on your calculator. You should have one, and you just hit the button and it'll pull up that number pi. You know, we have a 1, we have a 2, we have a 3, we have a 7. We've got all the numbers on the calculator. They actually have a button that's pi. So you hit it and pi comes up. So you do this, pi times 5 squared, and you get something like 78.13 or something like that. You've got 25 times 3.14. So you get this thing. That's the area. What that means is that if this is in inches, if this would be 5 inches, and you drew a grid like this, and you actually wanted to know how many square inches it would take to cover this thing, well, it's not going to be even. You see, you have little portions of them here, and a small little guy there, and half of one there, and a little bit there, and almost a full one there. and so on and so forth. How many of them are there? It turns out that there's going to be just over 78 of them. And so that pattern is really effective because you don't have to go and count all these guys up. They've given it to you, as with many other shapes that will be found in your textbook. And you'll notice we're measuring, if this were in inches, this turns out to be inches squared. So we're measuring that two-dimensional flat surface there.
To the boards! Hello and welcome back to the boards. Yikes! Look at all the questions we have on this board. Woo! We're working on formulas, and we want you to get some good practice here. So I've got 5 questions for you to work on at the board. As you do these 5 questions, make sure to go over these 3 procedures for each question. Step number 1. You're going to need to find or create the formula for this question. Be aware, formulas can be found in section 2.2 of your textbook, so if you're needing to find them, you can look there. Step number 2, you need to plug in the given values. Lastly, in step number 3, use order of operations to simplify and combine like terms if needed. Go ahead and pause the video and work on these 5 formula questions. Again, take a look in section 2.2 if you're needing a formula. Once you've worked the problems out, go ahead and unpause the video and we'll work on them together. Good luck! Okay, welcome back. Let's work on question number 1. You put $300 into an account that gets 3.7% interest. How much money will you have in 6 years? Well, let's find out. Step number 1 is to find or create the formula needed. Now, the formula is in section 2.2. The formula for interest is A equals P times 1 plus R raised to the Y power, where A represents the ending amount, P represents the principal amount, or the starting amount, R represents the rate, and Y represents the number of years. Okay, so let's plug in the formula, this information into the formula here. I know that A is going to equal P, the principal, which is $300, times 1 plus the rate. Now, the rate right now is a percent. We're going to have to convert that to a decimal. In a decimal form, I move it 2 spots to the left, so it would be 0.037. And it's raised to how many years? 6 years. Excellent. You'll want to go ahead and use order of operations. We're going to go ahead and do the parenthesis first. I get 300 times 1 plus 1.037 to the 6th power, because you do parenthesis first, then you do exponents. So 1.037 raised to the 6th power gets me A equals 300 times 1.243. Lastly, we're going to multiply, so times by 300, and we get a final answer of $373.07. Yes, making the money. Okay, let's take a look at question number 2. You have pennies. Now don't forget, pennies are worth $0.01. You have some dimes. Dimes are worth $0.10. And quarters, they're worth 0.25 cents. We need to write an equation for the total value of money. Okay, so V equals, and let's see, a penny is worth 1 cent. So what I'm going to do is use P to represent the number of pennies I have. So it would be 0.01p plus, dimes are worth 10 cents. Let's use the letter D to represent dimes. And quarters, since they're worth 25 cents, we'll use a Q to represent them. This is the formula they're looking for in 2A. Now in part B, we can now use our equation to figure out how much money we'd have if we had 12 pennies, 17 dimes, and 8 quarters. We're just going to plug those values in. So 0.01 times 12, because there's 12 pennies, plus, how many dimes did we have? 17, so I plug 17 in for D. And since we have 8 quarters, I'll plug in 8 for Q. We can use a calculator to add that all up. And when we do, we get a total of $3.82. Excellent. Now in part C, it's a little trickier because they don't tell us how many pennies we have. They just tell us that we have X pennies, X plus 4 dimes, and Y quarters. Okay. So we're just going to plug those values in. V would equal, now I'm going to plug X in for the P. So I get 0.01X, because I have X pennies, plus 10 cents for the number of dimes I have. Now dimes is X plus 4. So I'm going to use a parenthesis here to represent that I have X plus 4 dimes. Plus 0.25, how many quarters do we have? Y quarters. Okay. Now we need to just use our order of operations to simplify. I'm going to go ahead and distribute the 0.1 in. When I do, I get 0.01x plus 0.1x plus 0.4. Again, I'm distributing this 0.1 into the parenthesis, plus 0.25y. Our last step then would be to combine like terms. I'm going to combine the x's with the x's. I get 0.11x. My y's with my y's. There's no other y, so I'm just going to get plus 0.25y. And then I just have this random 0.4 here that I'm also going to include. It's plus 0.4. That is the equation that they were looking for in number 2C. Moving on, let's go to the area of a triangle. Now, I went to section 2.2 and found the area of the triangle. Area of a triangle is area equals 1/2 times the base times the height. So let's go ahead and plug in these values. It says find the area if the base is 10 meters. So area equals 1/2 times 10 meters times the height, which is 8. Let's see, 1/2 times 10 is 5. And 5 times 8 is 40. So my final answer is 40 meters squared. Because it's area, and we had meters times meters, we get an answer of meters squared. Question number 4, convert 140 degrees Fahrenheit to Celsius. There's a formula for that, also in this section. C equals 5/9 times F minus 32. Now we know the F to be 140, so let's go ahead and write that in there. So it's going to be 140 minus 32, because that's what the formula says to do. Let's see, order of operations. Let's do parenthesis first. So 140 minus 32 comes out to be 108. So we have 5/9 times 108. So times it by 5/9. You can times it by 5 and divide by 9. We get 60 degrees Celsius. Woo! 60 degrees Celsius. That's really hot. Yikes. Last question. Find the area of a trapezoid when h equals 10, big B equals 5, and little b equals 9. Okay, to do that, we're going to have to find a formula in section 2.2. The formula is A equals 1/2 h, big B plus little b. Let's go ahead and plug in the given values. We know that the height is 10, so it's 1/2 times 10. Big B is 5, and little b is 9. Let's go ahead and work with our parenthesis. I have 1/2 times 10 times 5 plus 4 is 14. We can go ahead and use our calculator. 1/2 times 10 times 14 comes out to be 70. And because it's area, it's going to be centimeters squared, because we had centimeters times centimeters. And that's it. Woo! That was 5 tough problems using formulas. Hopefully going to the boards gave you some practice and time to see how this works. Feel free to keep working hard in this section. Thanks for watching.